we'll think about stability. Stability is quite a critical issue for engineer because designing a stable system is critical. So if we build a system and its continuous domain, it will appear like this. Then if A could be possibly, although A is matrix, let's say that this is scalar. So here A represents the state transition matrix, so how the system changes according to the state. So it's deciding the velocity of change. So here, for the most simple case, if x is like E84, then it's a solution of this differential equation. So if A is positive, we can see that it's diverging. If A is negative, we can see that it's converging. It's slowed down, decreasing. In this case, it's increasing. If A is nothing, well, it's just stationary something. So according to the A, the behavior changes. This case was, for example, nuclear power plant of Chernobyl. In Chernobyl, engineer designed the whole system in a way that A happened to be positive in some special cases. But that special cases was satisfied in that point, and it diverged. And it boomed. So it's engineer's fault. So this is scalar case, and if this goes to like this is vector case, and this is matrix. Here, similarly, we can see that the x is some kind of matrix exponential form. But now you know how to calculate E matrix A something. So we might be able to get the solution. So in the stability, when we analyze the stability, we have two viewpoints. One is whether a zero state, in other words, we put the system and it's starting from the initial condition 0 state, fully relaxed. And then we see given input, the system is stable or not. So here, because input can go to infinity, right? Input goes to the infinity, then state may go to infinity too in general, because coming energy is infinity, then internal state may, the energy of internal system may go to the infinity too. So we see that if input is bounded, for bounded input, we check the output is bounded too, bounded output. So we say BIBO, bounded input, bounded output, BIBO stability. So when we see the zero state response, we need to check whether the system is BIBO stable or not. If it's BIBO stable, okay, we may say it's stable. The other perspective is the zero input response. No input. Here, we mainly focus on A equal to AX, no input. Here, we see given the initial condition, whether the system will be stable or not. Here, given the zero state, given the zero initial condition, given the input, whether the output is bounded. Here, given the initial, there may be some specific initial conditions, something like that. Given this initial condition, whether the system is react in stable way or in unstable way. So here, it's kind of internal. We say internal stability. because it's a matter of internal something. Initial condition is internal something, and how am I behave from now on is internal something. There's no external thing. So we say it's internal stability. Also, we're going to cover one more topic. Lyapunov stability, that A transpose M plus AM equal to minus N. So given a system matrix A and given arbitrary N, if there exists solution M that satisfies this relationship, then we also can say it's stable. So we may use Lyapunov equation to check the stability of a given system. But you can see that here we analyze A or B, we just calculate eigenvalue and we check whether they are integrable, or we check the simple properties. But finding solution for this given differential equation, is more difficult. So its purpose of Lyapunov stability is not to check the stability, but to apply this equation for nonlinear system. So if a linear system, you check the stability like this. You just check the eigenvalues, and it will be okay. But if it goes to nonlinear system, you need to check the Lyapunov stability. If you're developing some controller, you need to prove the stability of your controller using Lyapunov theorem, something like that. So basically, this is for nonlinear system, nonlinear controller, but we will briefly cover the Lyapunov stability. And to cover the Lyapunov stability, we will see chapter 3.7 and 3.9. When we do the chapter 3, we skip this part, because these two parts are related to this part. So we will cover 3.7, 3.9 in this class, and we will see the Lyapunov stability in this class. So overall, you want to also here the stability can be checked by whether A is positive or not. For the scalar, you know what's positive, what's negative. But here, we need to think about whether vector is positive or whether vector is negative. Matrix. Then what kind of matrix is positive and what kind of matrix is negative? We need to define. That's what we say positive definite. And we will define positive definite, and we will say A is positive definite, a matrix when you cover 3.9. So from that definition, we can say whether a matrix is positive, or matrix is 0, or matrix is negative, using eigenvalues. Okay, so these are what we're going to cover today. Let's start from the first topic. Pivot stability. Bounded input, bounded output. If the input is bounded, whether the output is also bounded. So chapter 5.1. Input-output stability of linear time invariant system. Here we will see relaxed system. So let's consider LTI relaxed. means zero state, fully relaxed system. And the solution is, we already know that the solution is convolution. So time invariant system. So initially it was G tau and control input U tau d tau. This is for linear time varying system. But linear time invariant system, we were able to eliminate one variable and put minus. Actually there is comma nothing, but we skip it. So if time invariant, we can write like this. And fortunately, this is convolution form. This is convolution form. So if in convolution, you can change the order. G tau U t minus tau d tau. Okay, we have solution like this. Here, G is impulse response, right? G is impulse response. Okay, now this kind of linear time invariant system, let's consider U as bounded input U. So UT is said to be bounded if there exists some constant UM such that UT is bounded means it's smaller than UM. And this UM should be smaller than infinity for all T. This is quite natural definition. Then we say UT input is bounded. Now let's see when the output is bounded. So we define Bevel. Our system is said Bevel stable. This is bounded input, bounded output. Bevel stable. If for every given bounded input, if the output is bounded, then we say the system as Bevel stable. So Bevel stable is for bounded input, the output is bounded. So theorem 5.1, a seesaw system. Seesaw system is single input, single output, scalar system. A seesaw system is Bevel stable. If and only if GT is absolutely integrable. And 0 to infinity. In other words, from 0 to infinity, GT, if we take the absolute value, if it's absolutely integrable, there should be some m that bounds this value, which is smaller than infinity for some constant m. The proof is very straightforward. Just writing down y, and if u is bounded, and G can be bounded, then Y can be bounded, right? Proof is very straightforward, so I'll just write down YT is integral 0 to infinity, 0 to t, input G tau U t minus tau d tau. Then it should be smaller than absolute of each. Absolute of G tau, absolute of U tau. And this is bounded, um. Then this is smaller than um. And here, this is smaller than m. So this should be smaller than um. Therefore, output is bounded. The proof is very straightforward. Or we can show a anti-example that if GT is not absolutely integrable, we can show that it's not bivostable. In other words, if GT is not an absolutely integrable, this means 0 to T1 G tau d tau is larger than some specific constant n, then if we give a input in a way that 1 minus 1 when g tau is positive and g tau is negative, then our output yt1 is so if this is positive, then it's 1. If this is negative, then it's minus 1. Positive 1, negative minus 1. Then minus, minus, plus, 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 plus. So it's the same to absolute of g tau. If we give bounded input like this is a very well bounded input like this, then we can see that this will not converge because this is larger than some. This is not absolutely integrable. Okay. So here we set bivostability. The smaller scope is output bounded. Here, theorem. Okay. I didn't write down the definition of bivostable. Okay, and the smallest scope is output converges to nothing. But if we think about this case, for example, in the textbook, they give an example like this. A very special case though. For specific t, I will not write it down. Okay, bivostability means it's smaller than infinity. Smaller than infinity. And bounded means smaller than some constant. And output goes to nothing means output is finally equal to nothing as time goes on. So, bivostability does not guarantee that it's smaller than some specific constant. It guarantees that it's smaller than infinity. This is an example here. If we have this weird function, we can show that it's bounded. But the total summation is not bounded. This function is weird like this and goes like this. So the output, we cannot find some specific m, but we can prove that it's smaller than infinity. Of course, this is the best case. Now, let's state theorem 5.2. If a system with impulse response GT is stable, then as t goes to infinity, the output y excited by constant input, then it will approach, y will approach yt, here g hat is Laplace transform. Laplace transform of impulse response. In S we put 0. So if GT is stable, then if time goes to infinity, okay, if GT is stable and we give constant input, then as t goes to infinity, the output will converge to input times g hat 0. Impulse response is Laplace transform with s equal to nothing. And the other one is the output excited by a frequency response. With specific frequency, omega nothing t, for t equal to positive, the output will converge to, as t goes to infinity, absolute g, j omega nothing, hat sine omega 0 t plus theta with theta tangent inverse imaginary part of g, j omega nothing, real part of g, j omega nothing. Okay, it's a little bit more complex. So consequently, this means if input is sinusoidal input, with specific frequency omega 0, if a sinusoidal input goes in, then in the transient part it could be complex output may be generated according to the system. But finally, eventually, the output is also sinusoidal with the same frequency. Given a system, if I give sinusoidal input, then if this system is Bibo stable, this LTI system is Bibo stable, in the beginning it may show this kind of input. In the beginning, the system may show a weird response, but eventually it will show the same frequency output like this. This is the same to here. If I give a constant input, In the beginning, it may show this drastic, but finally it will converge to some scalar multiplication of the input. So this is for the red case, this is for the black case. Here, G, here this term, G hat is in general GS. This is G alpha plus I beta. So if I put alpha equal to nothing, then it becomes a sinusoidal input, GI beta. So instead of beta, we may put omega nothing. Then it's this J omega nothing hat. And this is phase lag or phase leading. So it could be, phase could be slightly different, but fundamentally omega nothing, the same frequency output yielded. Let's prove it. Number one is easy to prove. YT is because input is A, input goes out of the integral and G tau remains. And let's send t to infinity, then yt is integral from 0 to infinity a g tau d tau. Here we may add e minus 0 tau. Then the definition of the Laplace transform is small g in the text. This is definition of Laplace transform. So this is Laplace transform with s equal to nothing. Therefore, this is a Laplace transform with s equal to nothing. Straightforward proof. Let's prove the second thing. Second thing is slightly more complex than first. Input output is sinusoidal input. Okay, output is sinusoidal input. Then yt is from z to 0 to tau t, g tau, ut minus tau, sine omega nothing, t minus tau, d tau. Okay. So the final form is kind of a Laplace transform form. So we want to make it like this. We want to do the integration because Laplace transform is integration from 0 to infinity. We want to do like this. 0 to infinity integration for the same component and t to infinity component for the same component, minus. Then this is 0 to t, right? This is equal to 0 to t integration. So the first part, 0 to infinity part is 0 to infinity. Let's apply sine law to decompose it. Then g tau So this is the first component. And the latter component is minus from t to infinity g tau sine omega 0 t minus tau d tau. Okay, now what will happen if we send t to infinity? If we send t to infinity, this approaches to infinity. Then integration from infinity to infinity is nothing. So this will disappear if we send t to infinity. So as t goes to infinity, yt will converge to the first component part. In the first component part, this is function of t, so it can come out of the integral. And this is function of t, so also this can come out of integral. So that's why t will convert as t goes to infinity. We may rewrite sine omega t integral 0 to infinity g tau cosine omega tau d tau, the first part. And the second part is minus cosine omega t comes in 0 to infinity g tau sine omega tau d tau. Yt will converge to this value. Then we may relate those two terms to the GS. The Laplace transform is written like this. Here, as we did like this, let's put S as omega 0. Let's put S as omega 0. Then G, J, omega, its Laplace transformation is, by definition, 0 to infinity gt e minus j omega dt. Okay, this is Laplace transformation. So originally it was S. Originally it was minus st. T is missed. T. Okay. Then by using the Euler identity is what we say jewel of math. Jewel of mathematics is the Euler identity that describes this as sine and cosine. So this is gt cosine j omega cosine omega t minus, there should be minus, cosine minus j omega. Cosine minus j omega is equal to cosine j minus omega t is equal to cosine omega t, because it's even function. So cosine omega t dt plus j gt sine omega t dt, but sine is even odd function, so minus should appear one more time in here because of Euler identity. Cosine omega t minus j sine omega t. This is jewel of mathematics, and it really beautiful. Okay, let me say it after proving it. So this part is real part of j omega Laplace transform, and this part is imaginary part of j omega Laplace transform. So this corresponding to real part of Laplace transform, and this part corresponding to imaginary part of Laplace transform. So we can write it as sine omega t times real part of Laplace transform with j omega plus cosine imaginary part of Laplace transform, which is, in summary, the size is gj omega, because sine omega square cosine omega square is nothing. The size is size of gj omega, and it can be combined using trigonometric formula with some specific phase. Phase theta will be defined by tangent. So this is very, here E is a number when it's differentiated gives the same output. So it's a very special number, E, exponential. If we differentiate it, it's the same. Are there any number like that? That was the first question of E. And the result is, I'm not sure. So they found the number as 2.784 blah 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 blah. So this number 2.784 blah 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 is very special number. This number is kind of magic number of the universe. Why? Because this magic number E relates trigonometric function and imaginary number. So imaginary J and cosine and sine, fundamental frequency that describe frequency. This is complex imaginary number. And this special number E is basically they're different thing, right? Different thing, imaginary number, exponential E. Sine and cosine, they are in different domains, but three different domains are combined into one formula, and they connect, they make very harmonized something. By doing that, we were able to describe frequency component. This is basically frequency response, and this is time, this is frequency, this is about time. By doing that, by harmonizing them in a special way, they link the time information with the frequency information. So time information and frequency information is kind of the front side and back side of a coin, but human beings were able to take a look at just one side, just time domain. So we are living in time scale. So how old are you? 24, 25, time scale. Nobody asks you, how old is your frequency? Everybody asks, how old are you? Time domain. We are living in basically time domain. But beside the time domain, although we cannot see them, they are frequency domain. And this is very fundamental in engineering. This frequency domain is revealed by this formula, which relates three different things into one equation. So this Euler identity is what they say, jewel of mathematics. And everybody fully agrees that, wow, that's jewel of mathematics. How can that, how it happened to be? Wow, that's kind of secret universe. This number, wow, this number is secret universe. So, if you like this equation, you may name your children like 김27, second children, 김84, third children, 김52, like that. Father, why did you name my name like this? Because I love this equation. Okay, this is joke. So, we may able to calculate the number E. How to calculate this? We use Taylor series. I'm not sure, but let's try it. Using Taylor series, this is for, let's take A equal to FA plus F prime A, X minus A plus F double prime A. Here, X minus A square plus F triple prime A. This is Taylor series, right? Cubic, blah, blah, blah. And if we take A as nothing and X equal to 1, then X equal to 1, E equal to FA. This is E nothing, 1 plus FA prime. It should be the same. So 1 times 1 minus nothing plus, this is again, even though EX is differentiated, it's the same number. 1, X is 1, 1 square, 2, plus 3 factorial, plus 4 factorial, blah, blah, blah. So 1, 2, 2.5. Adding something, then it will make 2.7, blah, 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 blah. So you can calculate it, the magic number, using the Taylor expansion. Okay, so in conclusion, if a system GT is bivostable, then given the constant input, the output will vary, but eventually it will converge to constant. Given the sinusoidal input, the output will vary in the transient part, but it will converge to the same sinusoidal output with different phase. And we may utilize it for system identification. Okay, there is a black box system. There is a system, but we do not know what's inside because it's hidden or it's too complex. Hidden something, black box. Then we want to know how this is organized. We know that this is what kind of things are in it. Then you may put constant input. And if it gives constant output eventually, then you may guess, oh, this is LTI system, and this is bivostable system. Or if you give sinusoidal input here, and if the output is also sinusoidal, then this is LTI system, maybe possibly with very high possibility, and this may be bivostable. And in the black box, inside you may, in another case, you may model the black box. For example, if it's kind of robotic manipulator, there are various parameters. Then you give various inputs and take a look at the output, and you may identify the inside parameters given input and output. You can find some specific something inside the system. Here, one important concept is persistently exciting. To do that, we need to give good enough amount of various inputs. We need to give various inputs that fully excite the system, fully reveals the system characteristic. Then we can identify all the parameters in the black box. So that's what we say, persistently exciting. Just one input, we cannot see the all details. I think this is similar to human being, because human being is basically black box. Individual person do not know what's. If I ask who you are, then it's very vague question, difficult question. Who you are? I don't know. But somebody knows. I am blah, 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 blah. That's a person with system identification finished. To do that, we need to give various excitation. For example, play. Oh, I like play. Everybody likes play. Don't worry about it. Music. Oh, I hate it. You are not a musician. Acting. Okay, I like acting. Something like that. Engineering. Oh, I do like it. Precisely exciting yourself, then you might be observe your output and you might be identify yourself. Then, as engineers are, if as you know, if system is identified, engineering can do many beautiful things. Similarly, if a person is identified by himself or by herself, then she or he might be able to do much more better thing. So I think it's similar to human being. Okay, so this is about beaver stability. Although I have a few more things, let's do that after taking 10-minute break. Just integrate it. And if the output is bounded, then it's beaver stable. So that's the first method. Whether the system is beaver stable or not, try to integrate the output, and see it's bounded or not. And now let me explain second method that can check the beaver stability is using the pole. A scissor system with proper rational function yes. Proper function we mentioned in the last class, and rational function is functional polynomial without exponential or something like that. It's beaver stable if and only if every pole of its transfer function has a negative real part. Or equivalently, this means that they lies inside the left half S-plane. So if there's S domain, real and imaginary, if the poles, if we have a transfer function, proper and rational transfer function, for example, S plus 3, S plus 4 square, whatever. Let's say this is transfer function, and it's beaver stable if and only if every pole of this transfer function, minus 3, minus 4, minus 4. If they are in the left half plane, the real part, it could be possibly complex, but anyway, this real part is possibly they are located within the left half S-plane, then the system is Beaver stable. So this is second method to check the Beaver stability. Its intuitive validation is that if GS, its Laplace transform, has pole pi with its multiplicity mi, here one pole, two pole, its multiplicity is 2, then we may do the partial fraction which may result combination of pole like this. There could be possible some constants. Okay, it is multiplicity m, so s minus pi squared. Then its partial fraction may result linear combination of those functions. Then, to find y, we may do the inverse Laplace transformation of each component. Then, let's do the inverse Laplace transformation for any arbitrary s minus pi n, for example. Its inverse Laplace transformation is, you may remind what you learned when you were undergraduate course. It will be turn out like this. Remind back this formula. Laplace transform of Tn is Sn plus 1 n factorial. So, I made n factorial Sn plus 1. n factorial Sn plus 1. This will be Laplace transform to Tn. So, the first part will be Laplace transform to Tn minus 1. Divide by n minus 1 factorial, and this will result in e exponential pi t. It's coming from Laplace transformation. 증명 안 해도 되죠? This is coming from Laplace transformation, that Laplace transformation EAT FT is Fs minus A. Fs minus A, S minus Pi, if we do the inverse Laplace transformation, they will result in EAT. So this results in EPIT. This again from the table of Laplace transformation. Then take a look at this. Get this. There will be this form for n equal to 1, 2, 3, 4, 5, 7, like that. Then it will converge to nothing if pi is negative, right? If pi is negative, e minus something t, then it will converge. So you can see that if pi is negative, that means if this is s plus 3 square, like this, then the system is bibostable. So example, in chapter 1, we thought about this example, unit delay seesaw system. There was reference signal goes in, and A is multiplied, and control input goes to the system, and here was unit delay, and the output goes out and is fed back. Okay, we thought about this system, and we derived the impulse response as like 1 to infinity AI direct delta function like this. And we can see whether it's bibostable or not. So the first method is to integrate it. So we integrate from 0 to infinity gt dt, and 0 to infinity I equal to 1 infinity AI direct delta t minus I dt. And this, because the characteristic of direct delta, it will valid when t equal to I. If t equal to I, if I do integrate direct delta, it will be 1. So finally, it will be simply ai'th power. Then, this will either converge if a is smaller than 1, then it will converge to infinite series of 1 minus a absolute, if a is smaller than 1. If a equal to larger than 1, then it will diverge. It will not be bibostable. So, if this multiplication factor a is smaller than 1, then the system will be bibostable. Naturally, intuitively. It's well harmonized with our intuition. Another method. Find the transfer function. In chapter 1, in chapter 2, we derived the transfer function, and it turned out irrational function like this. Irrational function like this. Basically, there should be E minus S because it's delayed system. Whether if you remind the Laplace transform formula, you should remind that if there is unit delay, time delay, then there appears this kind of exponential form. And if there's a time delay, then the system is not rational. The Laplace transform is not rational. This is also unit delay system, so it's infinitely delayed time. So there should be some kind of this exponential form according to this formula. So this is irrational system, and the numerator and denominator, they are not polynomial, so we cannot find poles. So using this method, using this theorem 5.3, we were not able to decide whether this system is bibostable or not. Okay. Okay, so up to now, we thought about seesaw system. What about MIMO? Multiple input, multiple output system. if it goes to MIMO system. Fortunately, in the MIMO system, basically the same to SISO system, because in the MIMO system, there are multiple functions, multiple variables, right? For example, Laplace transformation. In the multiple MIMO system, there is G11, G12, G21, G22. There are many SISO systems. So in the MIMO system, if each of them satisfies this constraint, then the total system, whole MIMO system is bivostable. Similarly, if each component, this is method 2, if each of their poles are negative, then if they are satisfied for all each individual component, then the whole system is bivostable. Method 2. Method 1, if there's GT with individual components, 1T, 2T, 3T, 4T, if each of them is absolutely integrable, then the whole system is, MIMO system is absolutely integrable. So MIMO system is straightforward extension of SISO system. And let me think about the relationship with method 1 is time domain, method 2 is pole, but pole may have something to do with eigenvalue. So given system matrix A, if we know the eigenvalue of A, then we can analyze the stability very easily. So let's link the relationship between eigenvalue and bivostability. In conclusion, if all eigenvalues are negative, then it's bivostable. However, something could be bivostable, but some of the eigenvalue could be positive. So this is more strong condition. If all eigenvalues are negative, then it's bivostable, because we know how to calculate the GS from ABCD. It was determinant of SI minus A, 1, C, adjacent SI minus A, B plus D. This was the realization of this GS. Then pole is the root of this determinant, and root of this determinant is equal to eigenvalues. So basically, poles are eigenvalues. So if all eigenvalues are negative, then the system should be bivostable. However, we may think about this case, that poles are all negative, but one could be positive like this in the determinant, in the characteristic polynomial. But here, this term may cancellate it, possibly. Then, eventually, finally, it becomes stable. So there could be this case where some of eigenvalues are positive or equal to nothing, but still bivostable. One simple example is if B is equal to nothing, and CD is given like this, then A is 1, so eigenvalues is 1. So it's not here. It should be here or there. It should not be here. Eigenvalues is positive. But if we calculate GS, then GS is C. C is half SI minus A inverse times B. B is nothing plus D, which is 0.5. So if we calculate it, it will be bounded. It will be bibostable. So this is the case here where it's just bibostable, but all of the eigenvalues are non-negative. So up to this point, we thought about the zero state response. So if we do the Laplace transform for this is Sxs minus x nothing. But up to this point, we thought this x nothing initial condition to be 0. We thought this initial condition to be 0, and we derived this kind of equations. All those transfer functions, something like that. So we assumed the zero state response, and we thought about its bibostability given bounded some input. Given bounded input, whether the output is bounded or not. Now, we will go to zero input response. That no input, but there is initial condition. There is specific initial condition. Given this initial condition, whether the system will behave stably or behave in divergent way. So that's internal stability. This internal stability can be easily classified according to the eigenvalues. Take a look at the eigenvalue. You can easily classify the internal stability. Okay, questions up to this point? 질문 있어요? 자, 그럼 우리 eigenvalue의 세상으로 가봅시다. Internal stability, matter of eigenvalue. Eigenvalue, eigenvector, they are key in the engineering. So stability, internal stability. So sketch, let's do the first continuous case. The diagram is very simple. Okay, this is whole, unstable. No. Not like this. Not like this. Unstable. Okay, there are two stability. One is marginally stable, that bounded. The output is bounded. That's marginally stable. And asymptotically stable, that output goes nothing. So here, output goes nothing is the best case because we are thinking about internal stability. We're thinking about zero input response. So from the outside, nothing comes in. Inside, some energy is reserved in the system. So the best case is to remove the energy in itself, emitting the energy to the outside and making my system as stable as possible to zero state again. That's the best case. So if the output goes to nothing, we say asymptotic stable. So here, limit as time goes on, my state goes to nothing. Here, as time goes on, my state converges to specific constant. And if not those two cases, as time goes on, my system will diverge, unstable. So unstable, this is stable. In stable cases, one is marginally stable, the other one is asymptotically stable. And intuitively, from all the discussions up to this point, you may think about that it has something to do with eigenvalues. So if all the eigenvalues are what? All the eigenvalues are negative, then it will be asymptotically stable. It will make the excited state, initial condition is highly excited. But in the system, it's safely dissipating all the energies. For example, if there's a damper and spring, and I gave so much energies, so it's highly compressed. This is initial condition at t equal to nothing. Then, no more input. Then the system will, so there's energy is stored inside the system. But the damper will dissipate energy as heat to the outside. And finally, it will converge to initial state. So this is stable system, kind of. Asymptotically stable system. Or if we think about spring, only spring, if I compress it, it will not diverge, but it will oscillate. So it can be bounded, but it will not converge to nothing. Then the system will be marginally stable. What about unstable system? Can you imagine any unstable system in physical world? Maybe 연구기관. Those kind of things may be unstable system. 나한테 연구기관 개발했다는 사람들 이메일 왜 이렇게 보내는지 모르겠어. 좀 그만 보내요. 그래. 왜 교수들한테 계속 메일을 보내요. 연구기관을 세계 최초로 개발해서 특허를 냈습니다. 특허 내서 돈 버세요. 나한테 좀 보내줘. 교수들한테 그런 게 많이 와요. 찾아오는 사람도 있어. 옛날에는 어떤 분이 진짜 찾아왔어. 자기가 연구기관을 만들었대. 봐달래. 받아나 솔직히 모르고. 뭐 그런 거는 이런 거 있죠. 난 물리세계에서는 못 찾겠어. Okay. So here, what do you imagine? If eigenvalues are, if there's zero, eigenvalues zero, then they may stay on one point. Here, if eigenvalues are, some of the eigenvalues are positive, then it will diverge to make the system diverge. In more detail, it's just brief sketch. Let me write down the details. In detail, here all the eigenvalues are negative. Here, it could be 0, but in this case, algebraic multiplicity equal to geometric multiplicity. Means if there are two eigenvalues, lambda 1 equal to lambda 2, multiplicity, algebraic multiplicity 2, and if there are two eigenvectors for these two eigenvalues, then geometric multiplicity is 2. For two repeated eigenvalues, two different eigenvectors, then the system is marginally stable. Here, unstable is eigenvalues are positive or eigenvalues are nothing, but algebraic multiplicity is not equal to geometric multiplicity. What happened is there's two repeated eigenvalues, but there's one eigenvector, then the system is unstable. I will show an example. Okay, so if this is the case, you may imagine that the Jordan block, Jordan matrix, Jordan form may have only 1 by 1 blocks, right? If this is the case, Jordan block, Jordan form may have all the components is 1 by 1, J1, J2. All the components may be scalar. 1 by 1, 1 by 1, 1 by 1. 1 by 1, 1 by 1. If this is the case, then Jordan block, there should be some 2 by 2 or 3 by 3. In this case, if this is the case, for given one lambda value, there's just two algebraic multiplicity, there's 1 because there's one eigenvector. There should be Jordan blocks like this. So from the Jordan block, we can see whether the algebraic multiplicity is equal to geometric multiplicity or not. Let me see some example, some simple example. Let's start. Okay, if we take a look at it, you need to have some feeling that it seems like there are two eigenvalues repeated. It looks like Jordan block, right? Looks like Jordan block. It itself is already in Jordan block form. So, the eigenvalues are 2 repeated 0 and 1 minus 1. And there are 3 eigenvalues and 2 eigenvectors. So, algebraic multiplicity is 2 for this, but geometric multiplicity is 1, so it should be unstable. If we see, calculate it. Calculation definitely, directly shows that this is eigenvalue. And if we try to find the eigenvector, a minus 0i, some eigenvector, which is e1, e2, e3, eigenvector should make it nothing. Then the only choice is e1, nothing. C, nothing, nothing. So there's just one eigenvector. If we calculate the output is EAT. Output is EAT, so output is EAT, initial condition. Then you know the exponential of Jordan form. Calculate it. E 0t, t e 0t, 0 e 0t, first Jordan block, and second Jordan block e minus t. So So this guy is no problem, but this guy, t, makes problem. So if I give initial condition like 0, 1, 0, then t will survive. And as time goes to infinity, the solution also will go to infinity because of this t. So this is unstable system. Let's see this case then. Algebraic multiplicity is equal to the geometric multiplicity is, what we need to change is just removing the Jordan block. Let's remove the Jordan block like this. Let's remove it. Then 0, 0, 1. 3 eigenvalues and 3 eigenvectors. Then although eigenvalue is nothing, algebraic multiplicity equal to geometric multiplicity. So it should be stable. Right? If you calculate eigenvector there should be 2 eigenvectors for eigenvalue 0. Then we have 2 choices. One is make E1 as constant. If and only if E3 is nothing, then they are eigenvalues. So eigenvalues is C0, 0 or 0, C0. There are 2 eigenvalues, 2 linearly independent eigenvalues. So there are 3 Jordan blocks, 2 Jordan blocks for 1 repeated eigenvalues. Its output will be simply E nothing t, ET, E minus t. It should be minus, I'm sorry. E minus t, and here E0t, 0, 0. E0t is 1, 1, 1. And here 0, 0, 0, 0, 0, 0, and initial condition. For whatever initial condition comes in, it does not magnify it. Like t, there's magnification factor, no magnification factor, conserving factor, or decaying factor. So it will be marginally stable. Okay, this is for continuous case. For discrete case, basically the same. For discrete case, is marginally stable and asymptotically stable or unstable if all the omega values are smaller than 1. Here possibly equal to 1, but algebraic multiplicity is equal to geometric multiplicity. Here, lambda is larger than 1 or lambda is equal to 1 with algebraic multiplicity is not equal to geometric multiplicity. Let's say smaller, because algebraic multiplicity is always larger than geometric multiplicity. Whatever representation doesn't matter. Okay, so internal stability has something to do with eigenvalues. So up to now, we saw zero state response as Biot stability and So initial condition was 0, and just before we saw 0 input response, internal stability. So here initial condition is not nothing. There's some initial condition energy. So stability of those things. Now we'll see Lyapunov equation or Lyapunov stability that's useful for nonlinear system. So although this is linear system class, but we need to cover it so that when you go to your research area or if you handle the nonlinear system, you should be able to use the Lyapunov equation. So we will cover Lyapunov equation after taking 10-minute break. So any questions so far? 질문.
두 가지가 있는데 람다 S가 지금 뭔지
아이겐밸류들 람다 S는 람다 1, 람다 2, 람다 3 n개면 n개를 통칭해서 그냥 람다들 복수할 때 S 람다들
T가 S타입 보존이라고 말씀하셨는데 T가 0으로 되는 거
I'm sorry. 이거 인피니티네요. 그렇죠? 시간이 무한대로 갈 때 발산하냐 발산하지 않냐니까. And by using those results from those two subsections, we will use their property for the stability check of Lyapunov function. In chapter 5. Okay, first start from the Lyapunov equation. A Lyapunov equation is something like A. Given A is n by n, and B is m by n. So given n by n, m by m, they are linked through m. One in front and the other in the left back. They make another matrix C. This is a Lyapunov equation. Here, m is in the dimension of, because this is n, it should start from n, and it should end with m. So it should be n by m. M is n by m, and C is n by m. Okay, this is a Lyapunov equation. Let's see, for example, if n is 3 and if m is 2, what happened? Let's see what happened. Then there should be 3 by 3a, a11, a12, a13, a14, a15, 3 by 3, and b is 2 by 2, b1, b2, b12, bb, bb. And m is 3 by 2, m11, M12, M21, M22, M31, M32, and here I need more space. Okay, I may back it up. And C is n by m, 3 by, m is 3 by 2, right? 3 by 2, right. Okay, I skipped all the indexes like this. There should be some subscripts. But I write down all the formula, then I should be able to recover it in this way. A big matrix and M11, M12, M13, M21, M22, M23 equal to C11, C12, C13, C21, C22, C23. I should be able to rewrite this equation in this form, right? Because there are 6 equations. If I calculate it, there are 6 equations regarding C11, C12. And each equation we may rearrange it in this way. Then there should be some big matrix alpha. And let's say this M prime, for example. Then this is alpha M prime equal to C prime. This Lyapunov equation is written in this form. This is what it does fundamentally is some matrix, something like this. AX equal to B. So it can be rewritten as AX equal to B4, which is very familiar with us, right? Popular, just linear equation. AX equal to B4. So if A is not singular, given C, given C, if A is not singular, we can find unique M. This is familiar with us, right? So Lyapunov equation is given C, whether we can find unique M that satisfies this relationship. So it's linear equation statement. Given arbitrary C, whether or not we can find M, unique M, that satisfies this relationship. To be like that, M alpha, this big matrix, should be non-singular. So we will see when this is non-singular or when this becomes singular. So let's define. We need to define this matrix form as, let's say, like A. A, especially A written looks like T, but let me write different A. Let's define it. Define it as AM plus MB. So if I put M as an argument, then it appears AM plus BM. M appears here. I defined it. Then the Lyapunov equation is written as AM equal to C, according to our new definition. And also, let's define eigenvalue. Define an eigenvalue, this A, as given M, if there is specific eta that satisfies this, then let's call this eta as eigenvalue. If we think about the dimension of this matrix, alpha matrix, then its dimension is nm by nm, right? Here, 2, 3, 6, 1, 2, 3, 4, 5, 6. Nm by nm. So this is normal expression of eigenvalue and eigenvector. So in this operation A, there should be n times m eigenvalues. N times n, so in this case 6 eigenvalues. And it turns out that eigenvalue eta kth eigenvalue for k equal to 1 to n times m. This is summation of lambda I plus mu j, where lambda is eigenvalue of a. Therefore, I in this is from 1 to blah blah blah. A is n by n. And this is eigenvalue of B, matrix B. So J is 1 by blah 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 m. We can intuitively, briefly prove it. So, eigenvalue of this Lyapunov equation is any possible summations of eigenvalues of A and eigenvalues of B is eigenvalue of Lyapunov equation. Let's again, eigenvalue, we defined eigenvalue here. The structure seems to be the same, but this A is not matrix. This A is kind of new definition. You may consider what A is doing is like this. So fundamentally, what they are doing is the same, but to be strict, we need to define it. And its eigenvalue is any linear combination of eigenvalues of A and eigenvalues of B. Here's n eigenvalues, m eigenvalues, so this eigenvalue is n times m. Let's prove it intuitively. Intuitive verification. Okay, for A, let's think about eigenvalue lambda and eigenvector u. Normal eigenvalue and eigenvector. And for B, we may possibly calculate, in general what we do is like this, but we can slightly change the definition of eigenvalue and eigenvector in this way too. We can find this V too. There should be no problem. Changing the order, then we should be able to find this left eigenvector. This is the right eigenvector. So we can find those eigenvectors for each matrix. Then, if I add with this, okay, let me write it below. If I put uv in the parameter of this operation, then auv plus uvb. Here, auv is lambda iu, and vb is v mu j. So lambda I uv plus u v mu j. Scalar terms on here, which gives ax equal to a eigenvector equal to lambda eigenvector. So this is eigenvector eta k. So eta k is linear combination of eigenvalues of A and eigenvalues of B. So, to know whether there is a solution, unique solution M or not, we need to think about whether this matrix alpha is singular or not. So whether this A is singular or not. So possible case, one is non-singular. The Lyapunov equation is non-singular. Okay, first, if there exists no I and no J such that lambda I plus mu j equal to nothing. Okay, there's no I, no j. That makes this eigenvalue to be nothing if this is satisfied. And second, determinant of this matrix alpha. Determinant of this matrix alpha is product of all its eigenvalues. So, considering those two things at the same time, if I considering it 1 plus 2 at the same time, then the matrix alpha is non-singular. Non-singular if there exists no I and j. If this is satisfied, then its determinant is not nothing. That means alpha is non-singular. Okay? So if this is satisfied, then the determinant is not nothing, because nothing is not multiplied. 3 times 2 times 4, 3 times 4 times is not nothing. So determinant is not nothing, then alpha is non-singular. And if alpha is non-singular, given C, given arbitrary C, there exists M. Okay? If alpha is non-singular, then given arbitrarily C, there exists M. Right? Then, let me say, this is 3, 4. For every C, there exists unique M. Okay, this is AX equal to B case. If A is not singular, it's full rank. If it's full rank, then reminding the 4 fundamental subspaces, column space is in full rank. So all the B should be in the column space. So whatever arbitrary B, doesn't matter. Whatever B, it should be in the column space. And there exists unique solution because there's no null space. So there should be unique solution, AX equal to B, when A is full rank. So for every C, there exists unique M. If there exists no ij such that lambda I plus mu j equal to nothing. That means that Lyapunov equation is singular when if lambda I plus mu j equal to nothing for some I and j. Then for given C, the solution may not exist, or there could be multiple solutions. Right? If C is here, it's not on column space, then solution may not exist. Solution may not exist. If C is here, because there's no space, there could be multiple solutions. Okay, this is Lyapunov equation. Questions? Okay, then let's go to second topic, quadratic form, positive definiteness. Quadratic form, x squared. Okay, this is quadratic form of scalar. But what if it's a vector? If it's a vector, then we may write like this. Link two link vectors with Q. This is quadratic form. Quadratic form. And if X is vector, this is 1 by n, n by n, n by 1. And this becomes naturally scalar. So many times this becomes the cost function for various applications. So in your research you may see many times you will see this kind of quadratic form because this is scalar and minimizing this scalar is optimizing the system. So this is what we say quadratic form. And given this form, we can say by the property of this thing, we can say whether matrix is positive or matrix is positive or equal to nothing, or matrix is negative or matrix is negative like this. In conclusion, if for given non-zero vector x, for any non-zero vector x, if this is positive, then we say the matrix is positive. And that's what we say positive definite. If this is big or equal to 0, then we say the matrix itself for non-zero x, any non-zero x. Because if x is 0, this is definitely nothing. But for any non-zero x, if this is like this, then we say like this. Then we say positive semi-definite. If this is like this, we say Q is negative semi-definite. And if this is the case, we say negative definite. So by utilizing the quadratic form, we can say whether a matrix is positive or negative. Like scalar, as we say for scalar is positive or negative. Here we can say matrix is negative or positive. And in this section 3.9, we will always talk about symmetric cases. So we will state a few things on two theorems. And now let's begin. First, okay, all eigenvalues of symmetry real M are real. First statement. Okay, if I skip symmetric, then this is false statement. All eigenvalues of real M is not real. You can easily find real matrix M of which eigenvalues are complex. You can easily find it. But if it's symmetric, if it's symmetric, then real M symmetric matrix eigenvalues are real. We'll prove it. Okay. First, let's write a quadratic form. But quadratic form should not be written like this because eigenvalues on eigenvector could be complex number. So complex version of transpose is Hermitian star and given M, X. This is quadratic form in complex domain. And let's do the conjugate transpose one more time here. Then X conjugate, complex conjugate transpose. This is complex conjugate transpose. Complex conjugate transpose. So it's kind of generalized transpose. This is transpose for real matrix. This is generalized transpose. Then X transpose, M transpose, X. Okay. Now, we know that M is real. Because this is real, this is equal to transpose. Okay. And if it's symmetric, then it should be equal to M because it's symmetric. So what we see is that its complex conjugate is equal to itself. Its complex conjugate is equal to itself, which means that this is real. So we can conclude that X Hermitian MX is real. One thing. Now, X could be anything. So let's put X as eigenvector V, eigenvector V. Then, because this is eigenvector, this should be eigenvalue, eigenvector. This should be equal to eigenvalue and eigenvector. Scalar in the front, scalar in the front. We can write like this. From this, first, this is real. It's already proven. This is real, already proven. Second, this should be real. Although V is complex, V conjugate V should be real. Then, this is real, this is real. Therefore, it should be real. Which means that all eigenvalue of symmetric real matrix M is real. First statement, all eigenvalues of symmetric real matrix M is real. Proof of the first statement. Second statement, every symmetric, still symmetric, every symmetry matrix can be diagonalized. Here, the emphasis is real. Here, the emphasis is symmetry. Here, emphasis is symmetric, real. Okay, every symmetry matrix can be diagonalized. Using a similarity transform. Okay, what do you guess? I mean, without this, every symmetric matrix can be diagonalized using a symmetric transform. If I say this, then you may ask a question. The natural question is, what if there's multiple repeated eigenvalues, right? What if there's multiple repeated eigenvalues? Then we thought about Jordan forms or something. There was not diagonalization. There was different method. So you may ask the question. So that question comes in here. Even it has repeated eigenvalues. This is possible when it's symmetric. If the matrix is symmetric, then even when you have repeated eigenvalues, we still can make it diagonal form. 1 by 1 Jordan blocks. Diagonal form is simply 1 by 1 Jordan blocks. There's no 2 by 2 Jordan blocks or 3 by 3 Jordan blocks. Let's prove it. To prove it, we first define generalized eigenvector. Generalized eigenvectors of degree of grade n. Generalized eigenvector of grade n is this is definition of eigenvector, and generalized eigenvector grade n is here comes nth power. This is generalized eigenvector of grade n. Not only this, but also for, let's say, m smaller than n, it's not satisfied. It's not nothing. It's nothing when it's the same to the grade. So if you consider generalized eigenvectors for, let's say, let's think about M. Let's target the similar matrix M, symmetry matrix M, and let's assume that there exist grade 2 generalized eigenvectors. Generalized eigenvectors of grade 2. That means m minus lambda I square eigenvector is nothing. Let's say this is alpha. Beta is m minus lambda I. V is not nothing. Okay. If there exists such vector, then those two things should be satisfied. Now let's think about a little bit strange formation that m minus lambda I x transpose and m minus lambda I x. If you think about this transformation, this multiplication, then x transpose m minus lambda I transpose m minus lambda I x. Because m is symmetric, m transpose is equal to m. So it should be x transpose m minus lambda I square x. Okay. Now what happens is that if there exists such kind of generalized eigenvector of degree 2, then this is satisfied. Then by alpha, if I x could be any vector. If I put v here, m minus lambda I square v, m minus lambda I square v. So by alpha, it should be 0. The total, the whole equation should be 0 according to alpha. According to beta, m minus lambda I v is not nothing. M minus lambda I v is not nothing. M minus lambda I v is not nothing. Therefore, the total equation should not be nothing. According to alpha, it should be nothing. According to beta, it should not be nothing. Contradiction. Contradiction if there exists this kind of thing. That means there does not exist this kind of thing. That means all the eigenvector is degree, all the eigenvectors of grade 1. There's no such eigenvector grade 2 or grade 3, grade 4. All the eigenvectors grade 1. That means even there could be multiple eigenvalues. Okay, there could be repeated eigenvalues. So there could be algebraic multiplicity, duplication, but all the eigenvectors grade 1 means its geometric multiplicity is the same. So if I construct Jordan block, it should be 1 by 1 Jordan blocks. 1 by 1 Jordan blocks. All the component is nothing, which is form of diagonalized form. This is diagonalized form. Diagonalized form. Okay? So if it's symmetric, of course there could be repeated eigenvalues. Why not? But individual eigenvalue have corresponding eigenvector. So eigenvector, all the eigenvector of grade 1. So number of eigenvalues repetition is the same of number of eigenvectors. So if I construct Jordan form, then it will have 1 by 1 Jordan forms. If it have 1 by 1 Jordan form, that is diagonalization. So symmetry matrix can be diagonalized. Okay, now we can state theorem 3.6, combining those two statements. Okay, this is theorem 3.6. Okay, here was symmetric, here was symmetric. So symmetric. For symmetric matrix. Okay, for symmetric matrix. According to this, if it's symmetric matrix, then it can be diagonalized. Where D, this is diagonal components. It can be diagonalized according to this statement. And in the element of D are real, according to the first statement. If M is real, then its eigenvalues are real. That's what the first statement is saying. So the element of D is real. Okay, this is theorem 3.6. And according to textbook, order of textbook, we define what's the positive definite and what's the positive semi-definite and what's the positive negative definite. negative semi-definite. And what's the negative definite? Because I already told you in the beginning, I will skip it. And now I will write down theorem 3.7, which will be used in the section 5. This will be used in the section 5. 3.7 is a symmetric M by M matrix. M is positive definite. If and only if one of the condition holds. Okay, now still symmetry. Symmetry. Symmetric matrix X is positive definite by definition for any non-zero arbitrary vector. If it's larger than nothing, then it's positive definite. Positive definite. If one of the following conditions holds: 1, every eigenvalue of M is positive. This to be natural, right? All eigenvalues are positive, then symmetric matrix M is positive. Basically, we say whether it's positive definite or not for the symmetric matrix. Those terms are for symmetric matrices. So if M is being said to be positive definite, we can naturally think that it's symmetry. Okay, first, every eigenvalue of M is positive. Or all of the leading principal minor. Leading principal minor is for symmetric matrix. Leading principal minors is determinant of this component, and determinant of this component, and determinant of this component, and it goes on for larger matrix. So all the leading principal minor are positive. All the determinant of those things are positive. Then matrix M, symmetric matrix M, is positive definite. And if there exists a non-singular matrix N that satisfies this relationship, N transpose N, then this is positive definite. So this is very useful thing. This is what we say Kuocw decomposition. So if you give M inside Kuocw decomposition, they decompose this to N transpose N. This is very useful because when you program something, you need a special constraint that M should be positive definite. But because of numerical errors, sometimes it does not satisfy this condition because of numerical errors. because it's slightly modified by the numerical errors. It could be, some case it could be like this. Then what is good is to multiply it, let's say n. So numerically, what is useful is just multiply it n transpose n and make m. Then it should be positive definite. Then do the Kuocw decomposition. Of this m. Then you get another n, which is positive definite. So when you do the programming, many cases you will see some constraint that n should be positive definite, but because of some numerical errors, it's n prime, which is not positive definite, positive semi-definite. Then just multiply them like this, according to this. Then by this theorem, it should be positive definite. Then do the Kuocw decomposition to decompose it and find n, which is positive definite. This is one of the efficient way. Many times you will see that when you are doing research or optimization or something like that. Okay, anyway, so if one of the conditions hold, this is positive definite, or I can state positive semi-definite in the same manner. Bracket positive semi-definite. If every eigenvalue m is 0 or positive definite, then it's positive semi-definite. All the leading principal minor are 0 or positive definite. And this is slightly different. There is an n by n non-singular matrix. This or an m by n matrix n with m equal 10. Positive semi-definite is including this condition or a rectangular matrix n is also possible. It doesn't need to be a square matrix. Then it's positive semi-definite. So when we do the Lyapunov theorem, Lyapunov stability, we will use those properties. I hope to finish it within this class, but I don't have time. So I will start the Lyapunov stability in the next coming class.